All right, hi everyone. Is the volume too loud or is it just about right? Okay. All right, let's get started. So we finished off with SMT stuff last class. So today we're going to talk about the good stuff, the neural machine translation. And here's some logistics that you should already be aware of. Your assignment 1 is due this Friday. And there will be a final A1 tutorial, which is more of office hours. The TAs will be there, and yeah, if you have any in-person questions. All right, so before we start with NMT, let's do a quick recap of SMT, what we looked at. Historically, until the 2010s, SMT has been a huge research field. We discussed some SMT materials, but we didn't really deep dive into the full complexities of statistical machine translation systems. We looked at alignment, and you'll see why that sort of ties into some of the concepts we'll be talking about in neural NMT today. But real world SMT application, BEST systems were extremely complex and with many separately designed subcomponents with teams of engineers working on it, and required in compiling and maintaining large rules engine. Sorry, I'm just gonna, maybe this is better. Okay, so neural machine translation can be arguably said as the biggest success story of NLP deep learning. So circa 2016, NMT became the leading standard method for MT, starting with a fringe research attempt approximately 10 years ago in 2014. In 2014, the first seq-to-seq paper was published by one of UofT grad students, Elias Escobar. At the time, you may know of him as the chief scientist, maybe not anymore, but chief scientist as OpenAI, followed by a few other papers. Within a very short period of time, by 2016, Google Translate switched from SMT to NMT, and by 2018, it was everyone had, and it was the standard way to do things. Now, if you think about it, like within a span of just a few years, machine translation systems had switched from, systems trained by a small group of engineers in a few months that outperformed the state-of-the-art SMT systems built by hundreds of engineers over decades. Such that like NMT truly is a flagship task for NLP deep learning. And in 2024, the NMT research still continues to thrive with many improvements to the vanilla model that we're gonna go over today. So what is NMT? The first question can be that, what is the difference between SMT and NMT? Technically speaking, it's a false dichotomy because in both cases, NMT is also a model we're doing statistical probability learning. So we are learning some probability distribution over some variables. The main difference is that now we drop the noisy channel formulation. So remember that before we're doing, so far what we've looked at is we had this alignment model, so we're trying to find, with the noisy channel formulation, we had this alignment model, and then we have the target language model distribution. And in NMT, the main difference you'll see is that we get rid of that. We just focus on what's intuitive. Give some source sentence and give us the target language sentence. There are some research papers that still use noisy channel objective, but they're rare. When in our formulation, we'll focus or we'll default to this. Okay, so no explicit alignments, end-to-end training, and it outperforms statistical machine translation by a large margin. Now, the alignment problem we talked about, that's still there. So how do we solve that alignment problem? If you recall that in SMT that we discussed in last lecture, what we did was we declared an explicit alignment argument A, and we marginalized that, we came up with that alignment model, etc. But in NMT, what we're going to do is we're going to use what you call encoder-decoder or sequence-to-sequence encoder-decoder architecture, where the role of the encoder is to take a source sentence and encode it into a latent representation, and the decoder takes that latent representation and then decodes it into the target language, adhering to the syntax and semantics of the target language. So a question may arise that why do we need such an architecture? Why not just use, because we have looked at trigram models of language modeling. We've looked at RNNs for language modeling. So what do we did in language modeling objective? We fed in a word and we sample from the distribution of the probability of the next word token. So you can ask that, why can't we just do that for machine translation? Maybe just feed in a word from source language, feed in a French or Spanish word, and then basically just get the output word distribution in English. So the simple answer to that is that because of linguistic anomalies that we talked about in the first class. So on the left-hand side, you can see one example which is based on different morphologies. So here, if you have the input, our running example was Mary did not slap the green witch, right? So if you have the input sentence in La Bruja Verde, and then if you want to translate this, so you can still, from an RNN perspective, if you're just translating from La Bruja to the witch, it works, like, La, the, Bruja, witch. But then, the adjective and noun ordering in Spanish and French is not like English, where the adjective is coming after the noun, unlike English. So then you get Verde and you translate that to green, and you get an English sentence, the witch green, which doesn't make any sense, right? So this is just a simple example. Now you can argue that, okay, sure, then why don't we just use a bidirectional RNN to solve this ordering issue? But then even in that case, we have to assume that the source sentence length and the target sentence length are always equal, which is not the case. So, which is shown in the right-hand side diagram, where you can see the other part where did not slap, here it's just mapping to one word over here. So we don't know that beforehand. So we need an architecture that sort of allows us to, abstract away abstract away the source sentence length and the target sentence length, right? So this is the reason that we will look into sequence-to-sequence architecture, which takes care of these problems. So the encoder-decoder architecture is nothing like novel. It's just the same RNN blocks that we have looked at until now. And the idea is that here, the encoder on the left-hand side, it's going to encode some source sentence in French. And then you have the target sentence being and the decoders, sorry, I lost the feed here. I'm sorry, having some technical difficulties. So this is not going to.
That one part. So I think that's HDMI2. So you want that to be sent to
front projector.
And that's on side projector. Is that fine?
Yeah. Okay. All right. Thank you.
Okay.
Yeah. Sorry about that. Right. Okay. So we're at encoder-decoder. So the decoder's job is to take this input representation and then decode it into the target language, in this case, which is English. And you can think of both blocks as this RNN blocks or RNN layers, and with different tasks. So on the decoder side, what's happening is that the last hidden state vector of the encoder is getting passed on to the decoder as the initial hidden state vector for the decoder. And for the notation, everything that has a tilde on top denotes decoder components. And the decoder then conditions on the encoder's input and the generation of the output of the previous output token, and then generates the next output token. As you can see that the first token over here is shifted by 1 with a special token like start of sequence, because at decoder at time step, as the first time step, it hasn't generated a Y yet. So it's basically the first time step, it's shifted by 1, and then following that, everything like, whatever it generates is being fed back as an input to the next time step and the previous hidden state of the decoder, just as in the RNN case, as you have seen. And this is a very vanilla sig-to-sig model. There are many variants to it, just like everything else we have seen, but these are like the primitive components that should allow you to understand any other variants. So now, as you can see, that we've gotten rid of the noisy channel formulation. Our formulation is simply this, that you're given some source language text and you're trying to get the translation. You maximize the probability of our target language sentence. Okay? Any questions? So in a way, you can also like frame this problem as conditioned language generation, because we're generating a language in English, but it's conditioned on some other criteria, like the source text and the previous output tokens. Okay, so let's talk notations. So these notations we'll be using in the assignments as well. So maybe it's a good time to standardize or formalize the notations that we use going forward. Okay, so F, you can think of it as French, which is our source, which is going to be our source language. 1 to S is going to be the length of the source sentence, okay? As you can see that English is our target, and length of English, T denotes a separate variable, meaning that it doesn't have to be the same, okay? It's not going to be the same in most cases. Everything else is, yeah, so X is the input to the encoder RNN, and whenever you see a tilde on top, that means that we're talking about a decoder component. So X is input to the encoder, so it's 1 to S length, and X tilde is 1 to T, which is the length of the output from the decoder. H tilde is decoder hidden states, and if you see H tilde with the superscript L or N, it represents the layer, either layer or N as the number of heads. We haven't talked about heads yet, which we will in a second, but yeah, so L and N represents layers and heads. And P is just the output token distribution parameters, the probability parameters. Y is the sampled output token that's generated by the decoder. And the bottom 4 relates to attention, which I'll just defer to next few slides, but we'll skip this. These are all like attention context, which should make sense after we go through, after we cover attention. Okay, so quickly to deep dive on each component. So the encoder is given a source text X, and by TF, TF is basically like embedding function. So the T here represents a transducer, which basically means that for each input you're going to get one output. So this is an embedding function. So Fs is like a French sentence being given of length S, and TF is giving you the embedding vector for that Fs. Okay, and yeah, so the rest of them is pretty straightforward. So here you have the French sentence "Elle imite est magique," and that is going through this embedding function TF, and you're getting your corresponding input vector embeddings x1 to x4. Let's say here then our length of our input sentence would be 4, and at the last layer it's basically passing it on to the decoder. This is the hidden state vector at the last time step, or the last word of RNN, okay? And the decoder samples the target sentence word by word by the conditioned sampling, the conditional probability that we saw earlier. And it sets the input to the embedding of a previously generated word. Here TE is the embedding function of the output token that's produced. And here's a pictorial depiction at the bottom, what's happening. So we have the H4 coming in from the last slide, the encoder's last hidden state. And then we're starting things off with start of sequence token at the bottom, and x tilde x1 is the embedding of that, and then you create your h tilde 1, and you get your probability distribution, you sample your output. Take that output, fit that in to the next time step, get the x tilde, and then hidden vector, and so on. So that's the flow. Any questions? Yeah.
So how is the mapping, like the size of one sequence to the, for example, like the ETA machine would be like how many tokens would that be considered?
So.
Like it's not 4.4, right? Like, or is that how many tokens there?
Right. So the question is that what is the mapping between S and T, if I understand correctly, where S is the length of the source sentence and T is the length of the target sentence. So yeah. So the question is, how does the mapping happen? So that was the whole point. That here we don't really have to care about that mapping because the network, as we learn it from our corpus, implicitly takes care of that mapping, right? So everything is being encoder. The S and T, they don't have to have a direct relationship. So the encoder encodes everything into latent state, and the decoder job is to like decode that into some T that is learned from our corpus. Okay. Now you can, a related question could be that in your corpus when we're training, we can have a batch can have different sentences of different sizes, right? So this is one sentence, we can have another friend sentence which is like different S. So how do you account for that? So that is, what we do is, in a typical learning scenario, we use padding tokens, we take the largest size sentence in a batch, and then everything else is like sort of padded to make sure that it's like size S. So size S would be the largest sentence in that batch of that target language sentence, right? Recent techniques don't usually do that. We, instead of using padding, we do what we call we overlapped batching, where we just have a contiguous sort of sentence and we just truncate it to a size. But anyways, for the sake of our discussion, I think the padding in your assignment too, you'll be using padding, okay? So once we have this set up, how do we train the machine translation system? So we train towards a maximum likelihood estimate against our reference English translation. So we have a reference translation E, and we basically work to right, so if this is our loss objective, we're trying to maximize theta. So it's an MLE objective. We do this by minimizing the negative log likelihood. And we take the negative log likelihood, we take the negative log likelihood at each time step or each token generation, and we sum them up. So yeah, so for example here, you can see that we're summing up the total negative log likelihood, and then we're trying to maximize the objective that gives us the maximum, the best English sentence with the highest probability given the fringe observation. Okay, so now let's talk about a concept about teacher forcing. So in practice, what we do is in the bottom, so far I've said that, okay, so what we're going to do is that we're going to take the output of at one time step and we're going to fit it back over here, right? So that's what I've been saying so far. But in practice, what we do is we don't really use this. We take the reference English sentence and we instead feed that as our ground truth or as their output token at a time step, like from the previous time step. The reason for doing this is intuitively think about this. So let's say our output, friendship is magic is our reference sentence, and our decoder decodes at the first time step. Instead of friendship, it says enmity is magic, right? So let's just say that instead of friendship, you have enmity, something wrong. Now, if you output something not wrong, then you're feeding it back. Then it's sort of like a cascading error, right? Because now based on enmity, it's going to produce another word in the second time step, which is also wrong. And then you feed that back, and it's like an entirely different trajectory, right? So that's an intuitive way to think about it. So what we do is that we just, we don't use this. We do what we call a teacher forcing. We basically feed whatever is our reference, target ground truth from the previous time step. We feed that instead, okay? And one caveat to that is what's called exposure bias, is that our model is never allowed to fail in a way, right? So it never sees examples that are very, very erroneous, or something that it has like, a wrong example. So sometimes it makes it not generalize well to a failure situation, let's say. But yeah, but in essence, the concept of teacher forcing is this, that instead of feeding the output of the decoder generated output, we're feeding it from our reference sentence ground truth. Any questions? All right. Okay, so now let's talk about attention motivation. So in our formulation so far, we have talked about this earlier as well, that if we have a recurrent architecture, a recurrent layer here, all the information for the source sentence is being encoded and passed forward, and at the last time step at H5, this guy is supposed to contain all the information. And we've talked about why this can be difficult, because if it's a very long sentence, you kind of lose track of like, what's happening. So in the decoder, the idea of attention is that what if we could have, at each time step of decoding, have like a channel of information to each of the input word tokens or embeddings. So have like a connection to each of the word tokens in the input, and then try to like, assess that which of these input tokens are relevant to what I'm about to decode. So that's the idea of having an attention. And we'll call this architecture seek-to-seek with attention. So just an example here, you can see that this could be like a source sentence, and you have the translation at the bottom, and something in English like, or in French or Spanish, zone economic European would translate in a reverse way, the European economic area. And these connections, you can think of this as attention weights of tying, like, between source and target, that which token in the source was relevant to the decoding of this target token. And yeah, so this is sort of like a schematic figure to see that how the attention weights are working. Okay? All right, so now let's look at the mechanisms, attention mechanism in, let's formalize this. And now having said this, like there's a ton and ton of external resources that explains attention in their own ways, and it's kind of like very unappetizing for me to teaching something that there's like Tom's review of attention or something. But anyway, so this is my take, or this is our take, and feel free to like, see external references as well. So it basically has 3 steps. So first step, we're gonna look at, so the idea is that we will introduce an external, maybe I'll just do some writing here. Okay, so the main idea is that we already know this, okay? So x tilde t, so the decoder's input at time t, we have already seen this. We're feeding back the previously generated token or the ground truth, right? So the only thing new over here is that we're introducing a new context vector, ct minus 1. And how are we calculating this guy? So first, what you're going to do is that at decoder, we take each step. So decoder at time step t, we'll look at all the inputs in the source sentence. So what was the length of our source sentence? S, right? So we have a source French sentence of length 1 to s. So at time step t, we're going to look at all the source sentence 1 to s. And we will calculate some score, okay? So for each of the input source tokens, in reference to my current decoding step, I'll have a weight, okay? So something like 1 to s, okay? And then this is obviously not normalized. We do a normalization step. We do a softmax so that this is a valid probability distribution, alpha TS. And then we calculate the context vector by multiplying our input embedding, hidden state embedding, with their corresponding weight, okay? And the score function over here, there are many different score functions possible, but think of it, the most basic one is just a dot product, okay? And that's it, we get our context vector. Any questions? Yes?
How is the attention score related to the alignment score?
Very good question. So the question was, how is the attention score related to the alignment score? So in NMT, we're not doing explicit alignment. However, this attention score, as we'll see by the sort of attention table, gives us a sort of pseudo alignment matrix or pseudo alignment table that we can sort of relate, but it's not explicitly, it's not exactly the same as alignment. But if you think about if you do a presentation of source and target table with their corresponding attention score, and then you can sort of have a rough idea of the alignments. So it's related, but it's not exactly the same thing. We get that for free in a way from the process, but you can think of it as a soft alignment.
So what would be can there be any value?
Yeah, so I think it will make sense if we look at like a map, attention map, or let me finish this one and then, okay, so as I was saying that the score function variance, so you can have many variants of the score function for calculating the attention scores. So what I just gave an example was a basic dot product attention, right? So you're just doing a dot product of h tilde t, like the attention hidden state vector at time t with like the input, some input hidden state vector. But you can also have like bilinear attention where you can have like a weight matrix that you can learn. And yeah, so one mind mapping that would be helpful in coming when we talk about transformers attention is if you can think of the decoder hidden state at time t, h tilde t as a query, okay? And that attends to all the encoder hidden states, h to 1s, which are the values. So you don't have to, but thinking of it like this will help in subsequent lecture slides when we do transformer attention. So let's go through the pictorial example of attention. So we have encoder hidden state, h1 to h3. And let's say we're at time step 2 from a decoder. So first what we do is we take a score function for each of the decoder hidden states. So previous hidden state h tilde 1, we take a dot product against each of the input encoder hidden states, okay? We get our A values, attention scores. We normalize using a softmax. So we do a softmax function, we have a normalized function. And then we basically get the context vector by multiplying it with whatever the corresponding weight. And we have C1, and we concatenate this context vector with our previous whatever our normal input is, right? So here at the top bottom, at the top right, you have your new, x tilde t at time t, which is the context vector concatenated with your teacher forced embedding of previous output token. And we have if D is the dimension of our output token embedding, since we're adding a context vector, so it's going to be 2D. Does this make sense? Okay. All right, so now the multi-headed attention. Okay, so before I get into the slide with multi-headed attention, can I get a show of hand? How many of you have already know about multi-headed attention? Okay, so all right. So majority don't. So why don't I start with the first very intuitive understanding of multi-headed attention. So let's say the department wants to have a student feedback of me as an instructor, and they have you have to submit like a one-page paper, okay? And it cannot be more than one page. Like one-page paper, you randomly sample a student and tell him or her to write a feedback for one page. And so then I randomly sample someone and and then get the feedback of that student. let's say I get him and you know, he's reading Random Walk on Wall Street, we have something in common, so he gives me like a glowing review saying that, right, it's the best instructor he's ever had. And then I give it to the department says that, okay, so just one student maybe like have some more opinion, right? So I still have one page, and then I'm gonna say that, okay, I'm gonna include like 5 more students' opinion, okay? So, but each of them having 5 paragraphs in the same page. And then I randomly sample like 5 other students. And then all the other 5 students also like says that I'm the best teacher that they have had in different languages, right? Maybe there's one student who says that he's good, he's not the best. But whatever, my point is that the second page with 6 opinions, same size, but anyone will agree that the second page has more information in it, right? Instead of having just one opinion. So that's sort of intuitively the idea of multi-headed attention. So far everything is the same. Okay, so I'm gonna do annotations over there. So first thing what we're gonna do is like, let's say we split into n heads, so we can have, let's say two heads for simplicity, right? And then think of these 2 matrices are just like transformation matrices that projects the original vectors into a more compact subspace. So you'll agree that if I have a matrix of size d into d by n, and if I multiply the original you know, hidden state vectors, h tilde s or h tilde, then I'm gonna get a more compact values for my hidden state vectors, which are now the size, if n is 2, then it's half the size. Everyone's with me? Okay, so now we have a compact size. Now for each of this compact hidden states, I can calculate the attention scores, right? So now I have 2 context vectors, but each of them have the size of before of an original context vector, right? And now I'm gonna just combine these 2. Now the question is, what is the value of my new context vector here? What is this question mark value here? What is the dimension of this CT minus 1n? What is the dimension of a single head context vector? It's given here, right? So if my n is equals to 2, then I haven't reviewed this slide, so we'll be just like, we'll have an awkward silence if I don't get an answer. So my question is, in number 2, what is the size of my context vector here? What is the dimension? My original context vector dimension was d. Yeah, d over 2, because we have 2 heads. Thank you. What's your name? Thank you, Stan. Okay, so d over 2. All right, so then, Stan, so then what should be, oh, I've marked it too much. What should be the value of this here? So we're concatenating, like we have 2 heads. Sorry? Yeah, so there's d and d. And then in a single head situation, our size of our x tilde t was 2d, right? So the point is that even if we're using multi-headed attention, we're keeping the size the same. But as I argued earlier, like we have a 1-page review for me, but then it has more information. So if you look at the bottom right over here, then with multi-head attention, we have like the same, you know, overall architecture. The dimension-wise, the same is same, but the information content is better. Does that make sense? And yeah, so I think another question or another concept that I've found students having problem with is that how does doing this give us, like, how does this guy using 2 heads have more information content than just using single head, right? So yeah, so this year I sort of wanted to do like a quick code demo because I know that these things are very abstract, but if you see it in code, sometimes it makes more sense. I've already done the whiteboarding. Maybe I can still try to do it. Okay, let's do this. Um, okay, so can everyone see the screen? I mean, read it, read the numbers. Okay, so we haven't covered self-attention. So let's say this is a single head attention. Okay. So for a single head attention, this is sort of like you have a single head attention, and then we will do a multi-head attention. So the multi-head attention will be this guy, the self-attention, but like 2 of them or 3 of them or 4 of them. Okay. So here I say that my number of heads is 4, and all I care about is okay. So I have a single head attention, and D in is basically the dimension going in, and this is key query, don't worry about it. The only thing you need to know about is D out V, which is the output size, right? So D is the output size of the embedding that comes out. So let's say I have a sentence that has 10 tokens, okay? This is the original sentence, and what we get back over here is 10 by 4. And 10 by 4 because my output dimension with a single head is 4, right? That makes sense. 10 by 4. Does that make sense? 10 tokens, 10 by 4. Now, let's do multi-head attention. So multi-head attention is basically just focus on this line over here. Oops, that was not necessary. Anyway, the point is that now I'm going to have 4 heads. Okay, and like in the forward is just going to go through each of the heads and whatever. The goal is to show that the output embedding is different. So if we have 1 head and our output embedding size is 4, then we have some context vectors, and yeah, so our context vector is this with single head. Okay, and this is the same as MHA1, means multi-head attention with just 1 head. Okay. So the multi-head attention with 1 head is the same as a single head attention. Agreed? So if you look at this guy over here and compare it with this guy, you'll see that they're the same. Everyone with me so far? So basically what I'm trying to say is that if you have a single head attention, and if you have a multi-head attention with 1 head, same output, okay? Now, I'm going to increase the number of heads. So now I have a number of heads is 4. Remember, this step is necessary, but I'm not going to do it because I'm going to make a mistake. Now, multi-head attention 4 is basically a multi-head attention with 4 heads. Okay? Everything else is the same. So if I do this, then I see my context vector is of size 10 by 16. The reason is that you have 4 heads, each with like size 4, then I didn't divide it, so it's like 4 times 4, 16. So I'm going to correct this. Let's correct this. So here I uncomment the problem that I did before, and I'm going to just redo the same thing. And now my context vector size is 10 by 4, okay? Now here's my point. This is the context vector with multi-head, like 4 heads. And now if you compare that with our original single head, you can see that they're different vectors. Sorry, this. So context vectors using 4 heads minus context vectors using single head, there's difference. They're different vectors. So the reason is each of the self-attention. So we go back to our declaration of the self-attention module, right? So in the self-attention module, see these parameters over here, right? So these are random parameters, and then you do some kind of initialization, right, to give it like normalize it in 1 dot. But the thing is that when you have multiple heads, the value of this like query key, like the internal embeddings will be different for each of the head. So you're not going to get the exact same thing because they're each capturing sort of, because of this different initialization, different values of this weight matrices, you're going to get different information content. And thus, you're going to have like different information content with the example that I said, that if you have 1 page of paper, but you have different heads you're sampling from, you're not going to have the same sample, right? Because each head has different, each of you have different weight parameters in your head, so it's going to be different. Is this clear? Like, does this make sense? The problem with this class is that like there's a wide array of skills, spectrums. So it's probably this. Some of you is like, I'm really boring you out of your mind, but for some of you, I'm like, oh, what is this? So it's a little bit hard without feedback to. Yes, question.
So, kind of like, what's the difference between like is attention the only difference between like a multi-head like a model, like a multi-head attention versus just like a multi-layer and multi-objective?
I'm going to rephrase that question. So the question is, I think what the question is asking that what is the main difference between like attention-based model versus multi-head?
So like you have, on one side you have like a very like multi-layer perception.
Right.
Multiple heads. If you
Right.
just have like a multi-head, multi-layer
So here in this case, we're still talking in the realm of SIG-to-SIG, like RNNs with attention. So when we go to transformers, we'll also use multi-head attention, but in the realm of like there's no recurrent connection. There will be only just like attention. So the main difference, like there are more differences. This is just the attention is just one part of the overall architecture, right? So there's always differences, but I think the question needs to be a little bit more specific to which architecture, because when you say that we have MLP, that doesn't. I mean, it doesn't make. We can talk offline about this, but because there's a little bit of more parameters we need to specify. Okay. All right. Any more questions? Because this needs to be clear, and I don't want to see any. I mean, I would love to see not too many questions in PIADS on multi-head attention this year. Yes.
So, the multi-head attention only attends to the same amount of sequence as self-attention.
Yeah.
Only the sampling has increased.
Yeah. So everything is like, if you understand single head attention, it's doing the same thing, but on the same input sequence, on the same input sentence, right? So, but you're just using different, like let's say you're doing, instead of 1 time, you're doing it like 4 times with 4 different heads, like different initialized heads, and then you're joining them together. I think I've thought about it, and I think that my analogy with like, a 1-page review with 1 student versus multiple students seems like a very apt analogy to me, because it's exactly the same thing. You have the same amount of space, you have the same input sequence, and you're using just like the opinion of 4 different heads, and you're just putting them together instead of having 1 head doing, So everything else is the same. You're just like adding a few more heads. Yes.
From my understanding, correct me if I'm wrong, but in the single head attention, we're paying attention to the specific part of the particular sentence so that the decoder knows what to pay attention to, right? In multi-headed attention, what are we specifically paying attention to?
Yeah.
Like each head is paying to different part of the sentence?
Right. Okay, so good question. So for everyone, the question was that in multi-head attention, what is the difference between each head is paying attention to something, what is the difference? Yeah, so that's a good question. So the idea is that each of the head is capturing some kind of different patterns, you can think of it. So, there's no explicit rules that head 1 will do this and that, but if you look at some of the models, there's been some research where, like, let's say there's 12 heads in an architecture. For example, we'll see in Bartology papers where 12 heads, there's been some research to exactly answer that question or probe that question, that what are each of the heads doing. So it could be that 1 head is paying attention to where the sequence is starting or ending, like the start and end of sequence. 1 head head is paying attention to maybe the preposition, some preposition or the subject verb agreement. Another head, something else. So the idea is each of them is doing some kind of like pattern recognition, but each of them is different, and together they add more value.
So that is coming back to the that gentleman was saying.
Yeah.
That it's kind of similar to
It, yeah, it is. So single-headed and multi-head attention is like, from a technical perspective, there's no difference. It's just we're adding more information into our context vector. We're just making our context vector richer by having more opinions, or like, you know, more representation. It captures more geometric subspace patterns, right, because of different heads. Anyway, I think, yeah, so if you still have questions, then please use the office hours, but we have to move on for the sake of time. So attention advantages. Yeah, so one of the question was earlier that what is the difference between the alignment models and attention, right? So on the bottom right, as you can see that we sort of get some kind of like free alignment or quasi alignment. So if you line up like the source and the target, and this attention maps, this is like a heat map, right? Who asked that question about you? So if you think of this as like a kind of heat map, and you can see that you can call it like as a quasi alignment, because it shows you the weight or the connection weight between the source and target tokens. Yeah, so basically, like, yeah, solves the bottleneck problem and improves NMT performance significantly. So attention has its advantages. And we'll just briefly introduce transformer networks. So essentially, transformer networks, it was the breakout paper in 2017. Everyone knows about transformers. This is the underlying blog of all state-of-the-art language models or neural network models these days. The core idea of this was that, you know, just replace the recurrent connections with just attention only, and hence the title, attention is all you need. And the table 2 sort of shows its superior performance with less training cost and time. And we'll look at individual components of the transformers in lecture 6. Yeah, so yeah, maybe I can quickly go through the high level 3 minutes. Yeah, sure. So at a high level, the transformer architecture is such that you have encoder and decoder block. You still have the encoder-decoder block, and within the encoder and decoder block, you have some sub-modules. FFN is like fit for networks, and there's a self-attention, and then you have, on the decoder side, you have masked self-attention. And the reason it's masked is because we still have the autoregressive constraint that the decoder cannot see what's going to happen in the future, so we're going to have to mask the future tokens from the decoder. And cross-attention and FFN, at a high level, what happens is that on the left-hand side, the encoder, you get some input sentence. It just plays around with the input sentence, does self-attention with the same sentence, and percolates up the layers. And the decoder also does the same thing, so it just self-attention within itself. And then finally, with the cross-attention, there's attention between the source and the decoder. And finally, you have the probability distribution output for whatever, like in our case, the language model objective, or the machine translation objective, you have the probability distribution like you have seen. So if you like put this all inside a block, RNN block, sort of the input and output, they're the same, but inside, you have gotten rid of all the recurrent connections. And the reason, like an intuition for why this is useful is because if you focus on the bottom side over here, the left-hand side is a recurrent RNN architecture setup, and the right-hand side is a transformer setup. And here, see, look at H3. So in order to get to H3, we need to be at time step 3, right? Because we need to calculate H2 first, and H2 needs to know H1, and so on, right? But on the right-hand side, if you get rid of the recurrent connections, you don't have that constraint. So at the time step 1, you can H2 or H3 can calculate, like you can calculate H2 or H3. So in that way, you can have a lot of time step savings, right? So at time step 2, you have calculated H4, and the corresponding H4 would have taken like 5 flops or similarly, right? So because of the recurrent connections. So that's sort of the intuition of why attention-only models can improve on computation or efficiency. With that, let's stop it over here, and then next class we'll talk about evaluation and then your assignment and all the fun stuff. Okay, all right, thank you.